Yeah, that's better. So just a quick check. Can you hear me at the back of the room? Raise your hands. Perfect. So my name is Kuba, and I'll be introducing today's meetup. It will be just 5 minutes before we let the speakers in. We have 4 amazing speakers lined up for today's meetup. The first talk will be done by Veronika Maurerova, and she will be talking about customized loss function in GB and gradient boosting machine models. She's mostly working in H2O on machine learning problems. She's working on constrained k-means at the moment. So if you are interested in that topic, please come to her. The next speech will be done by Radovan Kavický. He's from Slovak. He's the founder of Slovak.AI, and he's co-founder of PyData community in Slovak. So he will be talking about Tableau extensions, API, and the future of AI. Then we will have about 20 minutes break or 15 minutes for some more drinks. The next talk will be from Yauhen Babakhin. He's our Kaggle Grandmaster and data scientist in H2O. And it will be about, as you see, the general pipelines for computer vision problems. I'm interested to see that. And the last talk will be from Václav Košár. He's from a company called Time is Limited, and he will be talking about fast stack vector norms on, and I forgot what the acronym stands for, out of vocabulary words. I think it's something like that, but he will definitely know, and he will explain that to us. All the slides are available on our page. If you follow this link, you should go to our GitHub page where we upload our slides. And before we start the talks, I would just quickly introduce H2O.ai, which is the company behind this meetup today. We are a company based and founded in Silicon Valley, California in 2012. We have raised so far around $150 million. In the last round, we raised around 76 million, mostly led by Goldman Sachs in US. We have an open source and closed source product. Maybe you heard about H2O Driverless AI or H2O Free or Sparkling Water. We have around 150 data scientists and distributed data engineers around the globe. And we are expanding quite a lot. This is one example. We have opened the office in Prague around 1 year and few months ago. And it was just me here working remotely. And 1 year after, it's 20 more folks here working. That's kind of amazing growth for me to see. And we have offices also in London, India, Singapore, New York, for example. Our HQ is in California, Mountain View. This is how it looks in California. I didn't mention we are hiring, but I'll get to that slide. So if you would like to visit this place at some point, you can apply. That's a nice visit. This is after our last meetup in Prague. This was our almost full crew back then. I think it's 10 more of us now. Quick introduction to our products. I think the people who will be talking from H2O, they will introduce it a little bit better. I just want to be really quick. We have the H2O, which is our first original product, H2O free open source, and it's in-memory machine learning platform for distributed model training and algorithm trainings. We have bindings for Python, R. We have Flow, our user interface called H2O Flow. The next product we have is called Sparkling Water, which is what I'm working on, and that product is basically integration of H2O and Spark. We try to bring the power of our machine learning into Spark environment. It's also open source. The third product we have, among other products, is H2O for GPU, which is Python project, mostly built for really fast machine learning algorithms on GPUs. So these are all open source. People often ask us how we get paid for these. We have people pay us for enterprise support. We have also some closed source product, for example, Enterprise Steam, which is a product which can help companies to deploy Sparkling Water H2O and basically H2O.ai products into production, into deployment. And it takes care of security, user management, and so on. And we have also Driverless AI. You may be heard of that product. It's an amazing thing which is used for automatic feature engineering and model training. You just upload data set and it will take care of it itself. You don't need to worry about that much. You just have the free knobs to specify how much time you want to spend on the model, how much accurate you want to be, and this black box will take care of it for you. It's not just a black box, we have machine learning interpretability, so you can of course see how the model performed, which path it chose, and so on. So this is a thing we are mainly working on right now. As our boss 3 is always saying, and we all agree with that we are trying to democratize artificial intelligence. What we mean by that we try to make artificial intelligence available for everybody. It should be free, everybody should be able to try some machine learning for free. That's why we have also AutoML, automatic machine learning, on our open source stack. We have also Driverless AI, which is free for academia and students and professors. This is just from our last investment round. Our boss 3 is seen here on US TV. It was really a big thing to us to see someone from H2O on a national TV in US. So it was nice. We have kind of few customers around the globe. We are starting to have more customers in Europe. I'm not gonna go through that list. You can go through it. We will upload the slides later. We are opening meetup groups around the world as well. Most of the meetups are in the US and in Europe, but as we open office in India, we are having more regular meetups in Chennai, Bangalore, Delhi, and we are also having meetups in Australia and Asia. As I said, we are hiring. You can read the positions here. I'm not gonna go through that. Basically, if you wanna try working on some cutting edge technologies with really interesting and smart people, we will be happy to see you. There is Petra, our HR person. She will be happy to tell you everything you need to know. And that's the last slide I want to show you. If you don't have anything to do on October 22, please join us in H2O World New York, where most of our developers will be speaking about their products. We will have also our customers speaking there about their use cases. I think it should be a pretty packed day at New York that day. And if you know Joe, he's a guy who's usually doing these interactions. He has some free tickets for you, so if you really want to go to New York and you don't want to pay for it, we have a solution for you. So that's everything from me, and I would like to welcome Veronika for her first talk.
Hello everybody, can you hear me? Yeah, it's okay. So let me introduce myself first. My name is Veronika Maurerova, and I'm a software engineer on H2O free open source machine learning library. Previously, I worked in Atacama and Sequenji, and I finished my master studies at CTU with specialization knowledge engineering. Today, I would like to introduce a new feature from the last release, which is customization of loss function for training gradient boosting machines model. First, I would like to introduce H2O open source library first. It's open source distributed library for data science, machine learning. We implemented a lot of algorithms, for example, deep learning, GLM, gradient boosting, random forest, and lots of others. And we are still improving our algos, and we also implement the new ones. For example, as you can see, in the last major release, we implemented support vector machines, Shapley values for the random forest algorithms. We are working on target encoding, and we also improve visualization and boosting algorithms. And we also introduced a new hot feature, which is customization distribution in gradient boosting machines. And that also means that users can specify own loss function, which is very important for gradient boosting machines algorithm. And now let me quickly explain how gradient boosting machines works. It's an ensemble model. Maybe for the first time, who knows gradient boosting machines? Yeah, a little guide. I have little time to explain it, so maybe there is also documentation and booklet you can look inside. So I just quickly introduce how it works, and it's more complicated, but I hope it will be enough for you for this talk. So it's ensemble model, which means it's composed from lots of weak decision trees. Do you know decision trees? I hope. The trees are learned sequentially on the error from the previous trees. So the error is specified by the loss function, which is what I will be talking about. So this loss function is optimized to get best trees and get the best prediction as possible. So the resulting model is combination of prediction from all these trees, from each tree. So you can, as I said, you can learn more in our documentation and booklet, and we have also the booklet on the table, so you can learn more about this algorithm in the booklet. So why loss function is important for the learning? There are sometimes some types of distribution which you can specify before start learning gradient boosting model, and depends on the distribution, the loss function will be selected as well. And it's up to you to select the right distribution before start learning, and you can do it, depends on your target data. You can look in the data and say, yeah, it's similar to Gaussian, it's similar to another distribution. So you can use some predefined distributions. For example, if you want to predict high of the males in the US, you should use the Gaussian distribution. Everybody know, I hope. With Gaussian distribution, the mean square error loss is coupled, so it's what it's optimized in the algorithm. And if you want to, for example, classify data, you have to use different distribution, Bernoulli distribution, where Bernoulli loss is used to minimize the error. So there are lots of another distribution like multinomial, Gaussian, Poisson, Huber. So you can look into how the distribution looks and decide which you select for the learning. However, sometimes the data are really specific, and you have to you want to customize the loss function, the loss calculation, because you know the data and you know where problem is, and you want to change a little bit the calculation of the error. So you can customize the function. For example, if you want to predict flight departure to optimize time the customer has to spend in the airport, if the prediction will be 10 minutes after the flight takeoff, the customer will be really angry because he missed the flight. But he's not so angry if he is at the airport 1 hour before the flight, because it's still better than miss the flight. So this error is important for the customer, so you can customize the function a little bit. Or for example, in logistics, if you have a shop and you want to optimize number of items in your shop, in your store, for you can be more important to have enough items in the store than if customer comes and no items are on the store. So there could be some example where symmetric loss function is not so good for the prediction. So now it's possible to do some changes in loss function in H2O from the last major release. So now I would like to demonstrate this functionality on really simple example in real data from Kaggle. The data contains information about sold items in several shops, and I process that a little bit. I add some new features, time lags, and some which is not important for the demonstration, but you can download this data on the Kaggle. And I customize the function to show you how it works. So you can, if you are more interested in this demo, you can download it on our website. It's IPython notebook, and every step is explained there in more detail. So if you don't get something here, you can go through again. So the goal is predict number of sold items in particular store for some next month. So it's regression problem because we want to predict some numbers. And for this regression type, for example, Gaussian distribution is useful, but you can use, of course, some others. But it's very simple, and everybody knows Gaussian distribution, so it's nice for demonstration. There could be generally two types of error. The first, there are fewer amount of items in the shop. So the customer who wants to buy something is sad because there's no items and he has to wait for it. And the second type of error is there are more items in the store, so it demands more space to store the items, and the manager of the store is sad. However, for some manager, it's more important to have happy customers, so he or she wants to have enough items in the store to predict the right value, and the second error is for him less important because, for example, he has enough space for the store the items. So if we set the distribution parameter to Gaussian, we got similar number of both errors. So we can see the Gaussian distribution of residuals, which means difference between predicted value and the real value. And for us, now we can see that the error is around 0, which means that's how mean square error works. It distributes the error around 0 and some errors on the left and some errors on the right in the distribution of how normal distribution works. So we want to change it, and we want to have more items on the one side to satisfy the condition that customers are happy. So in H2O, users can customize whole distribution or only part of it. Can you see the code, or is this too small for you? Okay. So as I said, distribution is useful for loss function calculation, but also for other things like initialization of prediction, in the first step of algorithm, or in the prediction transformation. However, usually users want to customize only the loss function because it's important for her, so for him. So he can only took the defined distribution and edit only the gradient function, which is important for loss calculation. And to penalize the positive residuals more than negative, we implement asymmetric loss. Like here we only multiply residuals by some constant. It's then multiply error. Yeah, can you see it or not? So it's a very simple example. It's not the 10 constant. The constant 10 is not smart, but it's only for demonstration that we can customize the function. So we can penalize the positive error to get the result that all prediction will be higher. So the manager will have enough items in the store, and customers will be happy because he goes to the shop and enough items will be in the store. Now, what happens? There are significantly more predictions which are bigger than the sold number. You can see in the green bubble that perfect prediction will be much higher than before. This is Gaussian distribution, and this on the right for you it's custom Gaussian distribution. So the error has this similar distribution, but is shifted to the left because we want to have more negative residual to achieve the goal. And yeah, but there are still enough some of underpredicted values, but not so much. So the manager will be happy. And there is a comparison of a residual analysis, the pure Gaussian distribution and custom Gaussian distribution. You can see that the residuals are shifted down because we want to have more negative residuals, and that's what we get when we customize the Gaussian distribution. And yeah, users in H2O can also customize metrics. So the smart solution is to combine these two features: customize distribution for training and customize metric for validation. For example, if you use these metrics as a stopping criterion. So there's also example how to upload custom metric, which is implemented a long time ago. And we also penalize as the same way. There is constant 10 multiplier, and it's the same way, but it's different functionality a little bit. And yeah, the results are similar. The residuals are shifted as we want. So if we combine custom distribution and custom metric, we can get again shifted residual distribution. And also variance is changed a little bit, and number of predictions which satisfy the condition is also high. So to summarize that, we use the simple loss function improvement, like we change only calculation multiplier by some constant, but the result is significantly changed, depends on the specific requirements or condition. So the possibility to customize loss function calculation based on data knowledge can be really important for people who work with data and can really improve their prediction. And if you have any question about it, you can ask. Thank you.
Question, you showed the distribution of the errors, the green and the red items. Does it mean that the red area in the custom distribution is 1/10 of the whole area under the curve? Because you use the factor of 10, so I would expect that the red errors weigh like 10 times what they actually are. Or is it not that direct?
It could be. I'm not sure now, but you can play with the function more and use more specific mathematical operation to get result. It's just for demonstration how it works. It's not so important how many the residuals are there.
So, in this case, what you want to find, so you want the distribution to be biased one way or another. You're kind of displacing it, and only when it makes sense, actually. Do you have another tool that you apply on top of it to find when it actually makes sense?
Sorry,
I'm not sure if the question was. So, in the example of the items in this story, as you mentioned, you wanted it to be negative because you're subtracting.
In this case, I wanted to be negative to demonstrate the negative residuals is more important, but you can specify different function where it's in the opposite way or completely different variance and different shape of the distribution, so you can change it.
Yeah, the question was more related to if you have other ways to find which distribution would best fit the data that you're evaluating.
It depends on your input data.
Yeah, exactly.
Yeah. And
so, for instance, you have an input, and in this case, the Gaussian solves the problem. If you shift it to one side or the other, as you did it there. But maybe a Poisson would be better, exponential. So would you have another tool?
Yeah, you could. Yeah, you can use another distribution and customize this distribution. It's so you can use Poisson and set some condition on the computation of the loss, and it could be used also for your problem. So you can completely define your distribution. If you know that there is some mathematical law inside, you can define your distribution and define four methods only, and it will be used during training and validation. Yeah, but this is just the dummy example to look inside and understand.
We have time for one last question from Veronika. I'll give you a microphone. We have improved since then.
So when I would like to customize loss function, for example, do I need to make sure that my custom loss function will be like the gradient of my loss function will be easily computed?
You have to. It works that you have Python code which is implemented into our backend, and you have to be able to write it in Python, and that's all. So if it's complicated and you know how to compute the loss, you just write it in the Python. And
so I also have to write the code for computing the gradient, or
sorry.
So do I need also to write the code to compute the gradient?
No. Just define gradient, the calculation of gradient, and it's used in loss function calculation. So if you know that the function has to have gradient, if the function has no gradient, there's no possibility to get inside the algorithm. It's okay.
Thank you, Veronika. It's a pleasure to give a talk today. So I will be talking about general pipeline for computer vision problems. A couple of words about me. I am a Kaggle Grandmaster, competition Grandmaster from Minsk, Belarus. I have gold medals in both classic machine learning competitions and deep learning competitions. And I have about 4 years experience in data science, and now I work as a data scientist here at H2O.ai in the Prague office. And today I'll be talking about the general pipeline for computer vision problems. So I have divided it into three big blocks. The first one is data preparation. Then you need to initialize your models and prepare for the training. And the third block is about the training the model itself. Alright, before starting any computer vision task, you need to define your problem. So here is on the slide presented some kind of the most popular problem types that you could find in computer vision. For example, the simplest and the easiest one is here on the left, is image classification. When you have some kind of images and labels,
and you need to detect what is located on the image. For example, here is a cat. A little bit more complicated problem is classification plus localization. Here, instead of only predicting the class of the image, you need to also draw a bounding box around this cat and to detect the region where the object is located. Another problem type is semantic segmentation. Here you need to assign to each pixel one of the classes, of the predefined classes. So here we could see, for example, grass, cat, tree, sky, and so on. Yeah, and another problem types is about multiple objects. It is object detection and instance segmentation. Here, instead of finding like all the dogs on the image, you need to find each individual dog in the image and draw either a bounding box around it if it is object detection, or a mask if it is instance segmentation. And once you have defined your problem type, it is time to get the data. If you're lucky enough, you could find some data on the internet already for your specific problem, but it is not usually the case. So first of all, you need to collect the data, and you need to label the data. So if you are solving, for example, like here on the examples, object detection problem or segmentation problem, you need to use some kind of tools that are available on the internet, or write your own tool just to make the process of data labeling a little bit faster. And you could either label the data by yourself, or acquire some domain experts or some people on Amazon Mechanical Turk to make this process faster. And also to more faster label your data, you could use this approach with active learning. It is usually also used with a human in the loop. When you have unlabeled data, you firstly select some kind of a random sample in the first stage from this unlabeled data and pass it to the humans. Humans are labeling some portion of this data, and you obtain some small labeled data. Afterwards, you can train a machine learning model on top of this data and predict on the rest of the unlabeled data. And now, instead of selecting like random samples out of the unlabeled data, you're selecting the samples that are like most complicated to your model, so where your model is most confident in. And afterwards, like repeating these stages, you're allowing your model to learn on the most complicated examples, and it improves with each stage the quality of the model and its kind of the generalizable power. And here is a plot that is presenting the advantage of active learning. Here is like gray-white dots are the points when you're just randomly selecting the data to be labeled. So here on the x-axis is the amount of labeled data, and on the y-axis is the model accuracy, and we see that for the same amount of labeled data, we obtain a better quality model by using this active learning approach by selecting more like the most unconfident examples from the trained data, from the, unlabeled data. All right, so once you have acquired your data, you labeled it, now it's time to split it into train and validation sets. First of all, you need to define some kind of evaluation metric. So it is kind of a number that will show how well your model performs on the test data. It could be some kind of business metric, or it could be maybe some classic metrics. For example, for classification it could be accuracy, for segmentation it could be dice score, and so on. And also to split the data, you have two options: either to use a simple holdout set, or use a cross-validation scheme that is presented here on the slide. And a single note here that for deep learning problems, you need to train a model for each fault split separately. So you can't use the weights from the previous faults because it will introduce the leakage into your validation strategy. But the good news is that if they could be trained independently, you could split all the faults into multiple GPUs and train all the models simultaneously. All right, so now we have prepared our data, split it into some train and validation sets. And now we could start initializing our model. So today I will be talking only about like deep learning approaches. So I will not cover any classic computer vision stuff. And so for deep learning approaches, the first and like the most important, I guess, step is to select the architecture of a neural net. Again, you have multiple options. The first one is just custom architecture. You could, for example, if you have some knowledge or some domain expertise that this particular architecture could work very well for your data, then you could just use it and and be successful with your data. However, there's also kind of a huge zoo of famous architectures that were already developed like ResNets, ResNests, VGGs, DenseNets, and so on. So you could select from them. And also, the last option is about narrow architecture search. So it is an approach when like you're developing a completely new architecture based on your data. So it's kind of a neural net that generates the architecture for another neural net that works like pretty good on your data, on your particular data. And here's on the right is an image from the recent new architecture called EfficientNet. Here you see like the number of parameters and the top one accuracy on the ImageNet. And here's also some like familiar points like ResNet, DenseNet, as I said already. And the interesting observation that this new architecture, EfficientNet, that performs really well on ImageNet, was also initially developed using the narrow architecture search. All right, so you have selected your architecture, and now you have to like initialize the millions of parameters your neural network has. And like the first approach is of course just to use Radovan initialization. However, it is always better to use some pre-trained weights from the other task, for example from ImageNet, and it really allows to achieve better results for a wide range of tasks, of problems, starting from some medical images to some even audio spectrograms could be also like, the quality could be also improved using the pre-trained weights from the ImageNet. So if you have like available ImageNet and available architecture that was pre-trained on ImageNet, definitely use it and it will improve your quality. Also your data could consist of a bunch of images with different shapes and sizes. But as an input to the neural net, you should pass batches with the same size. That is why you need to pre-process somehow all your images into similar sizes, into similar shapes. There are a bunch of approaches, but here is kind of the most popular ones. For example, the first one is simple resizing. So we have some kind of a fixed size, and we're just resizing all the images to this size. So here's under the right arrow is like just a simple resizing of the image. However, it doesn't work really well when you have really a lot of images with absolutely different aspect ratios, because it just breaks the structure. And that is why there is another approach called random crop. Here is on the arrow under the left, so it's a central crop from the image. So we're just again selecting the fixed size for the input, and we're just randomly selecting the zone the image from the larger images. And of course, these two approaches could be combined together. We could start with some random resizing, so to resize the image to some random range of numbers, and then apply the fixed random crop. Or on the contrary, we could start with some random crop out the image, and then resize it to the same size. And this approach is like a combination of resizing and cropping, allows to train your model in a way that it knows about like your objects in different scales and in different positions on the image. Also, except for, apart from cropping strategies, you should also use the augmentations. So it's kind of the techniques when you are, instead of passing to the neural network a single trained image, you are making some random transformations to the image. And in this way, you are just expanding the size of your trained data, and also allows to kind of grow the generalizable properties of your model. So the two main points here is that firstly, these augmentations should be like valid for your problem, for your domain. I mean, for example, if you have these road images from the car, of course there is no sense to apply augmentations that rotates the image, because it breaks the structure of your problem and like it hurts the model. And the second point is that if you are like solving the object detection problem or segmentation problem, then like you should transform and augment simultaneously the initial image and the masks and bounding boxes, like it is presented here on the image on the right. And also summing up the augmentations, it is worth mentioning some recent augmentation techniques that use not only their trained images, but they also use like the labels. So here is their image from their cut-mix paper, and here in the second column you see the MixUp augmentation. It is kind of applies the weighted sum of two images. So I mean, if you have two images of cat and dog, you just combine them, sum them together, and find the average, for example. And then you also average in the labels. And the model is trained now in these weighted averages of images and labels. And it appears that even such hard augmentation technique allows our model to achieve better results and be better generalizable. And this particular paper was concentrated on the cut-mix augmentation. It works. It goes even further, so it combines mix-up augmentation and cut-out augmentation. And now we just kind of erasing the whole patches of the image and replacing it with another image, and we're just obtaining this kind of weird cat dogs, but it still improves the quality of the results. All right, and before starting the training, we need to define a couple of more hyperparameters. The first one is optimizer. So you have like the choice like Adam, LGD, and so on. So probably Adam is like the safest option you should select, because even if you have defined a really bad initialization for other your hyperparameters or for your learning rate, then Adam will still train and achieve pretty good results. And there are kind of new and recent modifications to Adam that resolve some of its problems. It's Adam with weight decay and R-Adam. Another hyperparameter is loss. So generally it is the function that will be used to update your parameters during the backpropagation in the neural network. And usually it differs from the metric you have defined, like the business metric or some accuracy, for example. And you could, for each problem type, you have a list of predefined losses you could select from, so they're pretty common and widely used. And finally, you should select the batch size, so the size of the batch you will pass to your neural network. And the general suggest here is that you should use the largest batch you could use. So the larger the batch, the better. However, of course, it is limited by their memory of the GPUs. And that is why it is not really a good idea to train on some large images. It is better to resize them to smaller size and use larger batch instead. And that is why to improve, to extend the batch further, you have other kind of tricks. The first one is batch accumulation. So you are just not making the updates to the weights each step, but you are accumulating your batch, for example, for 8 steps, and only then make a single update to the weights. And so your effective batch size 8 times greater than a single step. Also, you could use mixed precision training. So it allows to utilize more memory and less memory, and you could allow to use a larger batch size. And again, if you have multiple GPUs, then you could create a data parallel model and to combine all the GPUs to train simultaneously with a larger batch size. All right, so we have prepared the data, we have initialized all the hyperparameters. Now we could start training the model, and you should always start with some kind of a baseline model. It is done in order to provide some kind of debugging for the whole pipeline. So it allows to see whether it works, whether your model works at all, and whether your pipeline is correct. And also it allows to get some baseline score for your evaluation metric. And for debugging, you have 2 options. The first one is just you need to visualize everything you can. So you should visualize the images that were obtained from the train generator. You should visualize what images were obtained after the augmentations are applied, and so on. So you need to be not to be blind and to see what data you're working with. And another idea is to try to overfit with this simple model to a small portion of the train data. So if you were able to overfit, for example, 16 images or 32 images of the train data pretty easily, and then your pipeline works good. However, if you can't overfit even to a small sample from the train images, it means that there is some kind of the problems there in your pipeline, and you have to find it. And on top of this baseline model, you start building some kind of more advanced models. You could change architecture, increase augmentations, and so on. But the main hyperparameter in the neural networks, I guess, it is the learning rate. So you need to select what learning rate you will train your model with. And here on the slide, I have presented a couple of learning rate schedulers. So it's not really a good idea to train all the time with a single constant value of the learning rate, because it is better to some kind of change it during the training. And one of the approaches here on the top left, as most commonly used, is called reduce learning rate on plateau. The idea here is that we are tracking the validation loss, and if at some point it doesn't improve, for example, for 5 epochs, then we're just reducing our learning rate by some factor and continue training. And it allows us to get to better local minima and to find the better model and the better results. However, the problem with such approach is that if you have found some kind of a bad local minima, then it is hard to jump out of it, because you're always decreasing your learning rate, and it's hard to kind of jump out of this bad local minima. And that is why these approaches with cyclic learning rate are used. So here represented some linear cyclic learning rate, cosine annealing, and one cycle approaches, and they allow to find maybe some other local minimas that could be better than your initial one, and jump around for multiple local minimas. And apart from this selection of the scheduling, you have also some kind of tricks you could apply for the learning rate. The first trick is that if you're using some pre-trained weights from the ImageNet, for example, then initially for a couple of first epochs, it is like a good idea to freeze all the weights of your pre-trained network, because in this way you do not allow in the first epochs to break the structure and to break all the features that were trained in this neural network, because the rest of the second part of the network is starting from the random initialization. And for example, if you have this ResNet34 model and we want to use it for image classification, then we're just freezing all the convolutional layers, and we're just training only on the fully connected layers. And it allows to save the structure of the pre-trained neural network. And the similar idea is covered in so-called discriminative learning rate. So it means that you're using learning rate that is different for different parts of the architecture. I mean, if you again have some kind of pre-trained architecture, then for the first layers, you could use very small learning rate in order not to break the structure of the filters there, because like these low features are responsible for some general stuff like edges in the images or simple lines. However, you could use a much larger learning rate for the end layers of the pre-trained neural network in order to allow your model to train more specifically for your domain, for your problem type. So yeah, like using discriminative learning rate also allows to not to break the structure that was learned already on another task. And finally, we should answer the question: how should we select this learning rate value? So we should select this initial value for our schedulers. And basically, if you, for example, using too large learning rate, then it could appear that your model will diverge during the training. And on the other hand, if you're using too small learning rate, then it could take forever to train a model, because it trains really slowly. And that is why here is a proposal that was made in Smith's paper to select the learning rate. And the idea here is that we start with a really low learning rate and increase it very quickly to a large value. So we're, for example, making 100 steps of the training, and we're saving the loss for each step. And here is like a sample images from this procedure. So we see that at some point, our loss is expanding, and it is going up. It means that from this point, our model diverges, and it's kind of the extreme point where we could use the good ranges of the learning rates. And their idea and the suggestion there is that we should select either the learning rate that is located in the steepest region, like here's on the image on the left, or it should be like kind of 10 times lower than the lowest value we have achieved during this 100 steps, like in the image at the bottom. All right, so now we just started training our model, and the very good idea is to try to log as much information as you could. So you should log all your losses, metrics, all your learning rates. So here's, for example, images from TensorBoard. So you could use TensorBoard for these purposes. Also, it is a good idea to visualize dynamics of your predictions on the test set. So I mean, afterwards you could see like when and what your model is learning at the images, and maybe like to detect why it is not learning anything. And also another useful piece of information is like model checkpoints. So for example, after each epoch, you could save the weights of the model and the model state, or you could save it only the best checkpoints, or for example, if you have cyclical learning rate, you could save multiple checkpoints for each cycle. And afterward, this information, of course, could be used to make the predictions on the test set, on the one hand, and on the other hand, if you want to continue training, you can use these checkpoints as a starting point for their subsequent training. And also, apart from changing only the learning rate during the training, it is a good idea to speed up the convergence to utilize the changing in augmentation strategies and changing in the input size of the images. So it is always a good idea to use fully convolutional architectures. It means that you could provide for such architectures any input size, and it could handle it. And that is why we could start with really small images and then gradually increase the size of the images, and it allows to kind of iterate very fast in the very beginning and to warm up the weights of your neural network, and then you could gradually increase the input size and train on the full size images. And also another idea here is we could make a similar idea with augmentations. So here on the x-axis is the number of epochs we have, and on the y-axis is augmentation strengths. And you see that we're kind of beginning with some very like small augmentations, just some horizontal clips, some color shifting, and it is also used to some kind of warm up our neural network and prepare it for more harder augmentations with some distortions, rotations, and so on. And the trick that helps here is afterwards, after these hard augmentations, it is a good idea to switch off the augmentations completely and to train only on the images, on the initial images without any augmentations. And it's kind of fine-tuning with a really low learning rate, and it allows to eliminate the bias that was probably introduced by the augmentations into your data. And this fine-tuning on the pure images, on the pure trained images, achieves a better generalization in the future. Yeah, and for sure you're not going to train the neural network forever, so you need to define some stopping criteria. It could be either the number of epochs, predefined number of epochs, or you could use the so-called early stopping. The idea is really simple. So again, you have your validation score, and at some point you see that it kind of doesn't improve, for example, for 10 epochs, and then it is a sign that now our model is overfitting, and it is better to stop training and apply early stopping at this point. So that's it. We have basically trained our model, and now we're making the predictions to the test data. And one of the ideas that almost always works and helps to improve the quality of your model is so-called test time augmentation. So instead of predicting a single test image, you are just predicting it together with some kind of augmented test images, and then you're averaging its results. And afterwards, you could obtain some kind of ensemble of multiple test time augmentations, and it achieves better results. These augmentations could be, for example, some crops, flips, rotations, or this kind of example of D4 group on the slide, where you're applying all the rotations and also all the flips possible. And of course, you could first improve your results with ensembling. So if you were training with multiple folds, then you already had some kind of an ensemble when you could have combine and average together the predictions of multiple folds. Also, it is a good idea to use so-called multiple snapshots. So as I said, if we were using cyclical learning rates, we could save the checkpoints, the best checkpoint from each cycle, and afterwards, instead of using the best snapshot, the best model checkpoint from the whole training, we could select multiple best snapshots from each cycle and average them together, and it also occurs that it achieves better results. And here is an image from the paper where this approach has been proposed, and the title of the paper is train one, get M for free. So I mean, we are now training only a single model, but we're obtaining a lot of good candidates for our ensemble. And of course, there's just usual blending and stacking could be also applied here on top of your single model. All right, so great. We have covered all 3 blocks. We have now the model that was trained on our data, and we could analyze our test predictions. So we're making test predictions, and for example, we could draw some kind of our true labels and our predicted labels. We could look at our business metrics. We could, for a classification problem, could look at confusion metrics, and so on. And like kind of my favorite approach is for a classification problem. It is called GapData, and it is presented here on the right. And the idea here is that for each class, you could obtain some kind of a heat map and the attention map where your neural network is looking while it is making a decision. So here is on the top, it is looking at the cat while predicting the cat, and like on the bottom, looking at the dog while predicting the dog. So it also allows you to kind of to see maybe you have overfitted to some regions of the images, or your neural network just don't recognize the cats at all, and so on. And here is the overall pipeline I was talking about today. So it consists of these 3 large blocks with some additional steps I was describing today. And actually it kind of not a linear process, but it is rather a loop. So after you have made one such iteration, you are analyzing your test predictions, and probably you're not really satisfied with the quality of your model, or you're not very satisfied with some metrics, and you're just return back in the very beginning, and you could tweak some kind of augmentations, or change the architecture, or try some other hyperparameters, and just go through this loop multiple times until you're just satisfied with the result. However, if you are still do not satisfied with the result, you have some kind of additional steps. The first step is again evaluated by ICE, so maybe your metric is not calculated right, or you're not using a good metric, and even if you think that like the metric value is very low, but when you're looking by ICE to the images, you see that the model is making pretty good predictions. Another approach is to train longer, so maybe you have applied the early stopping too early, and it means that if you are training this model longer, it could probably learn some more stuff from your data and improve the quality of the model. And again, if you are like your predictions looks like a complete mess, then it is a good idea to debug all your pipeline again and start from the very beginning. And again, if none of these steps works, then it means that probably you don't have enough data to train a neural network model, and it is a good idea to get more data and get more label data. Yeah, and finally, it is kind of all this pipeline I've been describing today is now being implemented in Driverless AI. It is H2O's product, and it's we have like kind of work in progress right now. We have prototypes already for automatic image classification, automatic image segmentation, semantic segmentation. So it uses all the ideas I have been describing today with some additional stuff. And basically what you need is you just pass your images, your labels, and as a result, it finds like the best set of hyperparameters, the best architecture, trains the best model, and returns it to it. And moreover, here you could also use not only the label data. If you have very low amount of label data, you could use a combination of your unlabeled data and labeled data, and we will try to increase the speed of your labeling using the active learning approach I have described in the very beginning. So yeah, that's it. Thank you.
Thank you, Yauhen. Does anyone have any questions? Is the presentation going to be somewhere online?
I guess we'll share the video, and so yeah, it will be shared.
How do you work with the bad classifications in the Driverless AI when you need to debug?
Do you mean if we have some new data that is like bad performing, or?
When we're providing the data and the labels and the classifications are not how we want them to be, what tools do you provide for debugging?
All right, it's an interesting question. So basically, what we are doing is once we get the data, we don't know like the expectations. I mean, the model do not expectations about the quality metric we're aiming at. So it kind of tries its best to squeeze like the best performance out of the model. And if, for example, you were like looking for AUC like 0.8 and model achieved only 0.7, then this kind of like the explanation from us would be like it is the best quality we have achieved from your data. So yeah, no tools for debugging. All right, any other?
Okay, thank you, Johan.
Okay, thanks.
Hello, I will be presenting, I will have a presentation about fast text and its vector norms and out-of-vocabulary words. I will visualize vector norms versus their term frequency or count. Then I will show that in certain way there is a similarity between fast text norm versus stream frequency to word-to-vec norm versus stream frequency. And I will also provide rather weak evidence, but some indication of the fact that the norm is correlated to context specificity, and also that not averaging over n-gram count can be a useful indicator, for example, for detecting non-English words. So I'm Václav Košař, I studied physics, now I develop software, I dabble a little bit in machine learning, currently I work for a time-limited startup. They do analytics of internal communications and analytics. The communications, for example, calendars, Slack, and so on, to optimize communication within the company. So first, I will start with short embedding intro. So words can be represented by vectors. Usually we use dimensions between 100 to 300. The representations can be derived statistically, but usually today are trained. For example, a very common, very popular model is can be seen on the right, where from the words around certain vector we can predict the word itself. And the model is very simple. We just do sum of the vectors and then dot product with the whole dictionary and find the word. Usually the vector norms are actually not used, but you can get sort of a feel of what they mean by the fact that there is this dot product at the end. So the bigger norm, the more probable of that the word will be selected or detected. So it's some sort of you can get a feel that there could be some sort of specificity about the norm. So why we use these representations? Well, because they are useful, they are easily used for downstream tasks, and they also can be used just by themselves. For example, there's this cosine similarity, which is basically the angle between the two vectors. Vector norm is the length of the vector, but the norms are usually not used. So when I try to look at the interpretations of the norms, I actually found that it's hard to find any research, but there is this one paper. It's for word-to-vec norms from Shekel in 2015. It's called Measuring Word Significance Using Distributed Representations of Words. By word significance, they mean the context distinctiveness of the word, how well the word predicts the context, the document or sentence. And of course, they mentioned that there's this document term frequency, which can be used with the global or corpus document frequency to basically do the same thing. That's called TF-IDF. But they claim there that the word-to-vec norms are actually correlated to the word significance as well when they trained them on a corpus and within certain frequency band of the word. So for example, they took this corpus about quantum mechanics, and within certain frequency bands, they found 3 words: inflation, as in space inflation, sitter, as in de-sitter, and holes, as in black holes. And they claim in the paper that that's because these words are very indicative of the few articles that were about general relativity in the corpus, and that's why the word vector length width together with term frequency can be useful. They also do this plot for their trained word-to-vec, and you can see with the increasing frequency, the norms go down, but with but at the other end as well. So there's this interesting shape, and I think that can be expected that the words with very, very low occurrence in the data set don't have opportunity to actually increase their norm significantly, but there's some middle ground there in their rather low frequencies, which take the highest norms. So how the fasttext works? So the fasttext is another word representation model. What they do in contrast to word-to-vec is that they don't embed just the word themselves, but they also look at the subsequences within the words themselves, and they do representations for them as well. And they do this for each word. So if they have this word in a vocabulary, they take the whole word vector, and then they add sum of all the n-grams within the word. And then they divide by the total count of vectors. So that's basically how fasttext works. Why to do this? It's because they get higher accuracy, and as well, if you have words which are not in the vocabulary, you can still use the subsequences of the words, usually in the words, to create still some vectors, still represented somehow into this 100-dimensional space, which is not possible with word-to-vec, for example. However, there's this asymmetry, right? So, if I think I can, I don't think I can show that. But you can see in the equation that there are 2 parts. That there's this whole word, and then there's this sum of the n-grams. So if you don't have the word in the dictionary, you have only the right side of the plus, and that creates this asymmetry. So later I use both these parts to create different norms and to study them, plot them, and do these toy experiments. I also collected 10,000 most common words in English to contrast them with the fasttext vocabulary, which is in the standard pre-trained model. Fasttext has around 2 million words in vocabulary, but actually most of them are, well, many of them are these artifacts, maybe some concatenated words treated as single word, and so on. So this is useful to visualize where the normal words lie. So if we do the plot and we use just the standard fasttext vectors, then we get the plot over there. On the vertical axis, there's a length of the vector or the norm, and on the horizontal axis, there's the frequency of the word. How they occur during training, or they count. There's this interesting clustering, there are 4 clusters of the common words. We can see those yellow points which represent them, and I'm not sure what exactly those clusters correspond to. Maybe it would be interesting to find out. Disadvantage of this is that the scatter plot was a little bit too scattered. So later, if you use different approach, you may get something more useful. So the second plot is where I display vectors where I use no n-grams. So I just use the whole word vectors. And you can see that the shape of the plot is very similar to the one for word2vec that was presented in this 2015 paper. And 10,000 most common words are sort of in rather narrow band. And what we can also see from few examples on the screen is that there is another hint of this norm is word significance within frequency band. And that's, when you look at the green point, that's drown, which is rather common word, maybe capitalized, but still. Then the second point higher above that, the red one, is some word alpine, which I don't know what it means, so it seems very specific. And then there's this number tel, which is concatenation of two words. So it's probably very specific, but it's not a word. Yes. And the third plot, first scatter plot that we'll present is this other approach, where I, instead of using only whole word vectors, I use only the n-grams, but with a slight twist that I don't divide by the n-gram count. And when I do this, I see this very narrow band of the common words. So you can see there's this horizontal yellow line, basically, where all the common words have their vector norm almost the same. And I use this later in an experiment. So how to show that there is really this relationship between vector norm and word significance or word specificity. So there are actually there are these two. You can call two words. They relate to each other when one can be hypernym and one can be hyponym of each other. So, for example, month is hypernym of January. And that means that the January is sort of like a subclass or instance of a month. And similar, it's for color. So I have pairs color red, color black. And the thesis is that the more specific words should have higher vector norms, at least within some frequency bin. And actually, when I took all the examples disregarding the frequency completely, when I looked at the norm, at the vectors where I used no n-grams, I used only the whole words, then this norm was actually predicting with accuracy of 77% which one is which one is more specific and which one is not. It's not, it doesn't seem to be perfect measure. Maybe if I had more data, maybe I think there's this data set WordNet, and if I really had both pairs always at similar frequency, I could actually compare them and maybe I would get better results. But even like this, there seems to be indication that there is this relation. So what's other potential use of the norms? So they seem to really carry some information. So we can use them as well for detecting common English words. So if all the common English words are located around this one line on the horizontal line with very similar norm, then if you look at the histograms, we could take some Bayesian approach and try to predict which word is English, which is not. And I did this simple experiment where I took 3,000 random pairs and concatenated the words, generated all possible splits, and just looking at their norms, I was able to predict with low accuracy of 47%, but it's interesting that you can actually do this with something that's not considered usually useful. So to conclude, I did these, visualized these fast text vector norms, showed you some nice scatter plots, and norms relative to frequency. There was this interesting clustering in standard norm. No n-gram norm was shaped similarly to word to vec, as could be guessed. And there's this weak evidence of word significance somehow to be related to the norm, and also not averaging over n-gram count, and in general not averaging over words just which would be just anonymized, seems to be a useful thing to do. Code is over here at GitHub, and I have a blog at here, vaclavkosar.com. So if you have any questions, that would be the conclusion. Yes?
Do I understand it correctly that the norm might be of use in this case? Because it is somehow, basically not somehow, it is directly related to the structure of the space itself, right? So the way you define your vectors, the metric of the space where these vectors are defined.
Yeah, that's a
related
norm.
Interrelated with the norms, right?
Yes, definitely. That's very common metric in the space, but actually usually we use this cosine similarity, or at least in the application I've seen. So it's not. Yeah, but yeah, you're right. Or what is other?
Just to understand what is behind this.
Yeah. Yes. Any other question? Okay, so I think that's all.